Alright, so this is physics, and we're concentrating on section B of the physics paper. The first question B1, the figure in the diagram showing the reading of a vernier calipers. First one, what is the reading shown in the vernier calipers? To take the reading on a vernier caliper, the first thing that you do is you need to consider the reading on the many scale and on the vernier scale. So this one which is on top is called the many scale. It is given in centimeters. The one which is down is called the vernier scale. So from the many scale, what reading do you get? So you are going to get where the zero of the vernier scale is starting. Okay. So if you see this is 5, this is 6. What number do you expect this one to be? This big line. What do you expect it to be?
5.5.
5.5. So when you are reading, you are going to consider a line which is below. Okay. So where this one is, where the vernier scale is starting, you consider this line which is behind. So what do you think that is going to be?
5.3.
So the reading on the vernier on the many scale is 5.3. And then I will go on the vernier scale. I'll just write VS. That's vernier scale. So you are going to look at where the lines are crossing each other. So to my lines, these two my lines which are down here. Look at a line which is crossing direct with the one on top here. Are you able to see that one?
Yes.
Okay. So what can be the reading? Now you are reading from the vernier scale. So you are reading, remember this is 0 here, this is 5. Mean that this is 1, this is 2, this is 3, this is 4. So our reading we want to consider there is a 3. Okay. So that is a 3 from the vernier scale. So when you want to do the reading on your vernier caliper, so we'll say reading is going to be the value on the main scale, that is 5.3 centimeters, and then plus you get the one which you've read on the vernier scale, that is a 3. Now you need to multiply by 0.01. So this is going to be 5.3.
So is
Yeah.
it always to multiply 0.01 or
Yes, you always multiply. Always. The value that you get on the vernier scale, you always multiply it by 0.01. Okay.
okay?
So if you add these two, you are going to get 5.33 centimeters. Don't forget the unit. So that is how you get to read. So if this was a micrometer screw gauge, the answer would be in millimeters. But this is a vernier caliper. It is in centimeters. So make sure that you put the right unit. Okay. The next question: convert the reading in A above to meters. So this reading that we have found, we want to convert it to meters. How many centimeters are in 1 meter? 1 meter has got how many centimeters?
1,100.
Okay. So a ruler has got how many centimeters? A 1 meter ruler. A 1 meter ruler.
100 centimeters.
So it's 100. 1 meter is always 100 centimeters. And then you are going to say x is equal to, you have got 5.33 centimeters. So you just cross multiply 1 meter times 5.33 and then x times 100. So that will be 100x. 1.5.33, that will be 5.33. Then divide both sides by 100. So x is going to be 0.0533 meters. So that is the answer in meters. No, you don't round off here. unless I've told you to. Now the next one, write the reading in B in standard form. So this is B. You want to write this in standard form. So when you want to write a number in standard form, make sure that the decimal is behind the first number, which is not a zero. So meaning that it should be behind 5. So it needs to move 1, 2 up to here. So then the answer is going to be 5.33, and then times, you always multiply by 10. Now, because it has only moved 2 times, you are going to set the power. When you are taking the decimal in this direction, you put a negative power, so it will be to the power negative 2 meters. If the decimal is going in this direction, the power will be positive. Is that okay?
Yes, yes.
And then how many significant figures does the Venya Calipas reading in meters have? So how many significant figures are in this number? This one here.
Four. Four, three.
There are three. So the zeros, when you have got a decimal number, they are not significant. So it's just three significant figures. Okay. So that is it for this question. Okay, so we are now here. A man of mass 75 kg on Earth goes to the moon where the gravitational field strength is 1.6 Newton per kg. What is the mass of the man on the moon? What do you think? If a man has got 75 kg on on Earth and then it goes to the moon, what will be the mass?
Apa tuwavera formula ya mass equals density over volume or
So you don't have any volume here. So meaning that you can choose that formula. Can only use it if there is volume. So mass is constant. It doesn't matter whether a person is on Earth, on the moon, on Jupiter, the mass is constant. So even on the moon, this person is going to have 75 kg because mass is constant, it doesn't change. The next question, what is the weight of a man on the moon? Now weight is going to change. So you can actually find on Earth and on the moon the weight of the person. Okay. So weight is given as mass times gravity. Then here let me write weight is mass times gravity. Now if you check, the gravity on the moon is 1.6 Newton per kg. So meaning if it is on Earth, the person is 75 kg. Gravity on Earth is 10. Let me just put the units also so that you see how they're going to be cancelling out. Okay, so this man is 75 kg. Gravity on Earth is 10 Newton per kg. So this kg will cancel with this kg. The answer is going to give us 750 newtons. But on the moon, the mass is still the same, 75 kg. But the gravity on the moon is 1.6 Newton per kg. So the kg and the kg here, they are going to cancel out. So all that remains here is just multiply 75 by 75 by 1.6. So that is going to give us
20.
120 newtons. So you see, on the Earth, a person is looking to be much heavier than on the moon. So this is the answer we want on the moon. The reason as to why a person looks much heavier on the Earth is because gravity is high. Okay, is this okay?
Yes, yes.
Okay. A light truck of mass 2000 kg accelerates from rest. So if they say it accelerates from rest, what's the initial speed of this truck?
Zero.
Okay, the initial speed is 0. And then it it accelerates at a rate. So when they tell you rate 1.5 meter per second squared, what is this?
Final velocity.
So this is the rate of acceleration. Look at the unit. This unit is for what?
Or acceleration.
This is acceleration. So they've also given you the acceleration as 1.5 meter per second squared. Calculate the force required to accelerate the car. Calculate the force required to accelerate the car. What do you think we're going to use for this one? So using Newton's second law, do you know Newton's second law of motion?
No.
So Newton's second law of motion tells you that force is equal to mass multiplied by acceleration. This equation you need to know it. So the mass here is 2000 kg multiplied by the acceleration, which is 1.5 meter per second squared. So if you multiply 1.5 by 2000, we are going to get, sorry, let me get to punch this again, 1.5 by 2000, we are going to get 2000. This is going to give us 3000. A force is in newtons. So this is going to be the answer. You see how they give marks? Very simple like that. You are continually getting marks like that. So at the end of it all, like it will be very hard for you to fail because you are gaining marks, a lot of marks on simple questions like this. Is this okay?
Yes.
Okay, next question here. Figure B3.1 is a diagram showing a uniform meter roof freely pivoted at its center. A Newton meter is hung 20 centimeters from the pivot. So this is the pivot here and the Newton meter is hung 20 centimeters. Okay. While a 4 Newton weight is suspended 40 centimeters from the pivot, 40 centimeters this direction. So the question is, all right, you've been told that the meter is in equilibrium. So let's consider the question. If the meter is in equilibrium, meaning that it is not falling. So the first question is state the principle of moments of a board. What's the principle of moments? What does it state?
Of course, can I say one of you answer?
Mm-hmm.
Clockwise moments equal to anti-clockwise. Yeah.
So that is it. Clockwise moments equal to anti-clockwise moments. Now the next one is calculate the reading on the Newton meter. Want to calculate the reading on the Newton meter. So if you consider this ruler like this, you only you don't have uh, like forces this side, right? You don't have forces that side. But this ruler is balanced. Now because this question we haven't been given the weight or the mass of the ruler, meaning that we are going to take it that the ruler is massless. Okay, we're going to take it that the ruler is massless. Now let me get again look at the question. Calculate the reading on the Newton meter. Okay, we want the reading on the Newton meter. So what is happening here is this. This Newton meter is the one which has balanced the downward forces here. Are you able to see that? Like if this like the Newton meter is there, it is reading the forces which are this side, like the weight exerted on that side. That is why the Newton meter is there, just to get to read the forces which are acting on the other side. So using the principle of moments, clockwise moments is equal to anti-clockwise moments. So from here we've been told we have got a pivot at this point, meaning that this is where we have got a support. Okay, we have got a support like this, like that. Now, uh, since we don't know, we don't have any other force this side, like we don't have any force that side. The only force that we have is in this side. So what you are going to do is you are going to find the moment, which is this direction where I've got a Newton meter, because we don't have any other force which is acting on this one. Okay, so from the pivot, this, you always consider the pivot. Take note, you always consider the pivot. Remember, this ruler is in equilibrium, it is not falling. So there is a moment taking it in this direction, and what will be making it to move in that direction is the 4 newtons force. So what is this? Is this clockwise and clockwise?
Anti-clockwise.
Okay, so let me find the anti-clockwise moment. Let me call it m1. Moment is given by force times the distance. So the force here is the 4 newtons force. The distance is 40 centimeters. So this is 4 newtons. Please always include newton units, and then times 40 centimeters. You consider distance from the pivot. So 4 newtons times 40, this is going to give you 160 newton centimeter. This is the anti-clockwise moment. Let's also find what would be the clockwise moment, m2, which is also given by force times distance, but this will be force 1, distance 1, so this will be force 2, distance 2. So now this is the one, if this one is going down, it is actually the Newton meter which is balancing, okay, which is balancing these forces going up, like that. So whatsoever the force that the Newton meter is going to be reading, that's what we are calling F2, and then multiply by the distance of the Newton meter, that is 20 centimeters. So this is going to give us 20 times F2, that will be 20 F2 centimeter. Now from the principle of moments, clockwise moment and anti-clockwise moment are supposed to be equal. So we're going to say 160 Newton centimeter is equal to 20 F2 centimeter. So I'm going to divide by 20 centimeter this side, also this side by 20 centimeter. So the centimeter cancels with the 20. Centimeter also cancels the centimeter. So therefore F is going to be, this 0 cancels with the 0 there. 2 into 16, that is going to be 8 newtons. So this is the reading that we are going to be able to see on the what? On the Newton meter. Is that okay?
Yes.
So always consider the moments going up should be equal to the moments coming down. So that is the same as clockwise is equal to anti-clockwise moments. Okay, state with a reason whether the Newton meter reading would increase or decrease when the 4 kg weight is moved to a distance of 30 centimeters away from the pivot. Okay, with reason whether the Newton meter reading would increase. So let's say, from what the question is asking us, let me first get to rub some things here. So let's say this one, which is at 40, was moved up to 30 here. Okay, up to 30. Do you expect the reading on the Newton meter to be high or to be low? So meaning that if I want to find moment 1, instead of me using 30, 40 here, I'm going to use 30. So the answer would be 120. So meaning that for me to find this F, I'm going to say 120 divided by 20. That is going to give me a 6 newtons. Has it increased or reduced the reading on the Newton meter?
decreased.
Decreased. So how can you answer now the question? What can you say? State with reason whether the Newton meter reading would increase or decrease. What are you going to say? So it
Uh,
would.
uh,
Uh-huh. It,
Abaana okutebunkana okupanga sentence.
okay, so it would do reduce. The reason is when you bring back the 4 newtons force, the moment is going to reduce. Okay, the anti-clockwise moment is going to reduce. So that will also make the clockwise moment to reduce. That is why there is going to be a reduction. Is that okay?
Yes.
Okay. A small hard ball of mass 0.14 kg is thrown vertically upwards. So vertically upwards means it's been thrown like this, straight up, okay, and reaches a height of 12 meters. So it reaches a height of 12 meters like that, above the point from which it was thrown. Capture the work done in lifting the stone uh, to the height it attains. Last time I talked about something which is falling like this, how to calculate the wake. How can you find the wake of something that is being thrown or something that is dropping? So wake is simply equal to potential energy of something falling, and potential energy is mass times gravity times height. Yeah, anytime you have got something going up, this is the formula for wake. So the mass of this thing is 0.14 kg. Make sure that it is in kg. Gravity is 9.8 Newton per kg, and then the height is what? 12 meters. 6 kg will cancel this case. So the answer is going to be Newton meter. Newton meter is equal to 1 joule. So all you do is multiply 0.14 to 0.14 multiplied by 9. Oh, actually, for you guys, you use 10 as the gravity. So multiplied by
Abaana
10.
but 9.8 afuna kwisa.
Yeah. So as we don't use 10, it's for you multiply by 12. So this is going to give you 16.8 joules. Energy is given in joules. Is this okay?
Yes. So yonsanga tuli ekitaka create work done whether ile ekitaka involve kirema pamoja n'okubeera pansi efomula yakubonkera.
Mm. But if something is going forward, then work is going to be force times distance. It's just that distance going up is height. So this is the same as force times height. And you know that force is the same as weight. So this is weight times height. And you know that weight is mass times gravity. And then times height. So this is how the formula comes about. You see that? Huh?
Okay. Yes, yes.
So what is the velocity of the ball as at the maximum height? Now, this ball has gone up. At the maximum height is here, it is no longer moving. So at every time you have got maximum height, velocity is zero. Like it's no longer moving at the maximum height, it will start coming back. So the velocity is zero. Okay, is that clear?
Yes, so once we are above that we their maximum velocity.
Mm. Maximum going up, the velocity is zero because it will not be moving on top. On a windy day, the same stone is thrown upwards with the same energy, but fails to reach the height reached earlier. Why does this happen like this? So the way you have seen it like that, when you threw it up, like it covered 10, it covered 12 meters going up. Now, if there is wind, you throw it with the same velocity, with the same force, you find that it only reaches maybe 10 meters when there is wind. Why do you think it is like this? Why does it not reach this high when there is wind?
Slow down speed.
So now explain that better. Hmm. How can you explain that better now?
Hello, and welcome to my video about how much money I made on YouTube. I know this is a topic that a lot of people are interested in, and as someone who has been creating.
Hmm? So there is air resistance. Okay, the air is going to be pushing the stone downwards. So air resistance reduces the speed at which the stone is going to be going up. Therefore, it can no longer reach the same height. That's okay? Is that okay? Okay, just a moment. Okay, so here the answer is air resistance. Huh? The air resistance is going to be reducing, like the air is going to be preventing the stone from going up. So because of that, it is going to reduce the speed at which it gets to reach on top. That is why it's going to fall very fast. That's okay?
Yes.
Okay, so question on waves. Figure shows a transverse wave. So if you hear of a transverse wave, it's a wave that goes up, down, up, down, up, down, up, down. So you say it goes perpendicular, or it makes 90 degrees to the direction of motion. The wave is going in this direction, but the wave is going up and down. And then you have got also a longitudinal wave. A longitudinal wave looks like this. That's how it looks. So it's a bit different from transverse wave. All right. So now let's consider these questions. Now you need to consider this when you move from top. So this on top you call it as a crest, and then the bottom is called a trough. So when you move between two troughs or between two crests, that will give you what we call the wavelength. Is that okay?
Yes, I'm listening.
Okay. So you are going to have one wavelength if you cover two troughs, meaning that for this one, i- from here up to here, this is one wavelength. The symbol for wavelength is this. Now you can also count a wave starting from here up to here. This is one wave, meaning that this is also wavelength. And then again from here to here, this is again another wave. From here to here, again another wave. From there to there, again another wave. From here to here, another wave. So if you have just something that goes on top, just this is half a wave. If it comes down like this, that is one wave. Okay, so here we have got one, two, three, four, five waves. Five waves. Find the number of waves There are five. Is it clear now to count the number of waves?
Yes.
Okay. Consider what is the amplitude of the waves generated in the figure above. So amplitude is how far the waves go. So the maximum they go this. That's what we call amplitude. So amplitude is 5 meters. That's how far the wave goes. Then the next one, calculate the speed of the waves above if the number of waves in figure 8 B51 are produced in 2 seconds. Now I want to calculate the what? The speed. If these waves are produced in 2 seconds. Now to find speed, how do you find speed? Speed is actually wavelength times frequency. Have you heard of this equation?
Yes.
Okay, you need to know it on waves. It's a very important equation. Speed is wavelength times frequency. Now remember, for this question you've been told that all these waves are produced in 2 seconds. They are produced in 2 seconds. Now we can also rewrite this equation. Okay, we can also write this equation. The speed is going to be equal to, now here you have got um to find the frequency. What is frequency? Frequency is the time taken to complete only one, like time taken for only one wave. Here we've said we have got 5 waves, and for 5 waves we've been told in this question to say they take 2 seconds. So now you want how many waves are going to take only 1 second. That is what we call frequency. Frequency is the number of waves per second. So 2 times x, that will be 2x, and then 1 times 5, that will be 5. So divide both sides by 2. So x, which is frequency, is going to be 2.5, and it's given in hertz. That's frequency. This is frequency. Okay, 2.5 hertz. What is frequency? Number of waves made per second. Number of waves made per second. And then the wavelength in this question, what is the wavelength from what we're able to see?
Atamaza.
What will be the wavelength here from what you're able to see? What's the distance from here up to here? That's what I'm calling as wavelength.
One.
Are you sure?
Please understand the question.
What's the wavelength? What's the wavelength?
Yeah, you answer.
Wavelength. Wavelength. I already explained what a wavelength is. The distance from here up to here. Nothing. Okay. So we should also calculate the wavelength. So you can see how many waves do we have here? Uh, uh,
One.
so 5 waves. What is the distance that they've covered?
Six.
Okay, they've covered
Yeah.
6 meters. Now, wavelength is a distance covered by only one wave. So we're going to say one wave is equal to wavelength. That's a symbol for wavelength. So just multiply 5 times wavelength, that will be 5. This is lambda, and then 1 times 6, that will be 6. So to remain with the wavelength, lambda, simply divide 6 by 5. And that would be
One point two.
1.2 meters. That's the wavelength. So now we come in this formula. Wavelength is 1.2 meters, then multiplied by frequency. Frequency is 2.5 hertz. Now hertz is the same as second to the power negative 1. So if you see someone writes 2.5 second to the power negative 1, it's the same as hertz. So now you multiply 1.2 times 2.5. This is going to give us 3 meters per second. So that is the speed of the waves in this question. Actually, the speed of the waves, that is the speed. Is that okay?
Yes, 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 yes.
Okay. So another formula that you could have just used, which is simple, is that speed is the number of waves divided by time taken for those waves. So you have got
So so muri pakusanga wave speed idachinja ni va ivanamka ni yaiko.
that's the symbol for velocity. So you want to calculate the velocity, it's the same as speed. Huh? So speed, you don't use s in physics, you use v. That's okay.
Yes, yes.
So you could have just said speed is distance over time. You already know this equation, isn't it?
Yes,
And you
yes.
already know from the question that we have here, the distance for all the waves is showing 6 meters. And then all these took 2 seconds. So this will just give you 3 meter per second. So which is the same thing, huh?
But here apparently they are so
Yeah. Now for that sake, because we are dealing with this topic, just make sure that you also know that one, okay? Figure below shows light in air striking the vertical side of a rectangular glass block at an angle of incident 60 degrees. So angle of incident is if you have this as a block, ca- can be a glass. This is a, and then here you have got air, here you have got glass. If it is in up, this is glass, and then this side there is air. We have got a straight line which we draw here, which makes 90 degrees to this boundary here. This is called the normal. This line is called the normal. So in this case, the normal is this line. So when light is coming from air, so air is less dense than glass, meaning that glass here okira umwera. So the air is more less dense than glass. So when you have got light coming from the air going towards glass, what is going to happen is uh, light is going to be refracted towards the normal towards. But if it was like this, if it was opposite, glass was on top and then air is here. When light is coming from glass towards the air, this will be reflected away, okay, away from the normal, away from the normal. You say now they are different.
production ko paano inataka madrag para
So when you are coming from something which is more dense to something that is less dense, light is going to be reflected away from the normal, away from this line. That's why you can see it is more closer to this line here. But when it's coming from a less dense region like air to glass, it will be going towards the normal, which is this one. Is that okay? Okay. So you need to know that because at times they're going to ask you to draw. So the angle between the normal, this one is called the incident ray. Incident ray. This is called the angle of incident, the angle of incidence. And then this is called when light bends. This is bending. This is called refraction. Refraction. Refraction is the bending of light. So this is called the refracted ray. Refracted ray. And this angle is going to be called the angle of refraction. Now, if you have got a boundary like this, like glass, and then you have got a normal, and then light comes like this, it hits this, and then it bounces. This is different. This one, you see, it was bending, it actually passed on this boundary, but here it's not passing, it's bouncing. So bouncing, this is called reflection, and then bending is called refraction. Can you get the difference between those two?
Yes, reflection.
Okay, very, very important. Refraction has to do with bouncing, refraction, bending. So, what is the refractive index? So, the refractive index is 1.6. Now, the question is, what is the refractive index? I can give you the formula, and then from there you can explain what it is. So, from this formula I've written here, what can you say? What is the refractive index?
Speed punch.
Now explain in words because you don't want to give an equation. I've written an equation, now put it in words.
Refractive nature copy
Mm-hmm.
the 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 ratio of velocity of
Mm-hmm.
light
Mm-hmm.
in a vacuum.
Mm-hmm.
Chapo, apenda
So refractive index is the ratio of the sine of the angle of incidence to the sine of the angle of diffraction. That's what you call refractive index. That's clear. The ratio of the sine of incidence to the sine of refraction. That's the refractive index. It's okay? So just use this equation if you forget to make the definition. So calculate the angle of refraction R. I want to calculate the angle of refraction. So you already know the formula here, so it will be very easy to calculate the angle of refraction. Okay, so we know that n, which is refractive index, is sine I over sine R. So they've already given us a refractive index of glass, that is 1.6. That is going to be equal to sine. The angle of incidence they've already given us, that is 60. Then divided by sine of R. We don't know R, that's the one we want to find. Now the sine of 60, just need to punch on a calculator. So what I'm going to do is I'll say this is over 1. So I'm multiply 1.6 by sine R, that will be 1.6 sine R, and that will be equal to 1 times sine 60, that will just be sine 60. So I want to remain with sine R, so divide both sides by 1.6. So therefore, this 1.6 cancels the 1.6. This will give us sine R being equal to sine of 60. The answer you get, you divide by 1.6. That is going to give you 0.5412. Now to remain with R, this is an angle. You are going to take the sine inverse. Okay, just take the sine inverse of 0.54. Because you had sine here, just take sine inverse, you are going to remain with R. Therefore R is going to be, let's see, sine inverse of the answer we have. So the R is going to be 32.8 degrees. This is the angle of refraction for this question. Is that okay? Okay. Now the other question is, what is the critical angle of the glass block? What is the critical angle of the glass block? Now, if you hear of the word critical angle, what happens is this. When you have got, remember I said when light is coming from one region to another, different things can happen. So I'm going to show you three diagrams so that you just understand something called critical angle. So here you have got a normal. So when light is coming from one medium to a less dense medium, what happens is light is going to be reflected away from the normal like this. Okay, it's reflected away. So you can see this angle. This is the angle of refraction. This is the angle of incidence here. So what happens is that when you increase the angle of incidence, this thing will also be able to bend all the way to be going much more closer to this line. There will be a certain angle that you are going to reach such that this reflected ray will be exactly on this line. In other words, this angle here will now make 90 degrees. So this angle of incidence such that the refracted ray, okay, is exactly on the plane. That is what we call the critical angle. Is that okay? Have you gotten that?
Never going to have penny, so angle of refraction, I kind of a first straight line of the critical.
Uh-huh. So if the refracted ray is on the on this plane 90 degrees, then the angle of incidence which you have here is called the critical angle. Okay, is that okay now?
Yes, yes.
All right. Now the question is, how do you get to find now this critical angle? So this will now give you n, which is the refractive index. It is now going to be equal to 1 divided by sine of c. This is the equation that you use to calculate the critical angle. Refractive index is 1 over sine c. Now the refractive index for this question have already been given. What's the value given? Did you record?
1.6.
Okay, so 1.6, that is going to be equal to 1 divided by sine of c. Now 1.6 is the same as 1.6 over 1. So what?
Sine C something formula.
That's the thing. So I'm going to take this on top, 1 comes down. If I swap those two, meaning that also 1 is going to go on top, this one comes down. So I'm going to have 1 divided by 1.6 is equal to sine c divided by 1. I've swapped them. Now sine c divided by 1 is simply sine c. And then I'll divide 1 divided by 1.6. 1 over 1.6, that is going to be 0.625. So to remain with c, I'm going to take the sine inverse of 0.625. So therefore c is going to be sine inverse 0.625. That is going to give us 38.7
7 degrees.
degrees. So this is the critical angle for